welcome to this session on thread internals and related design patterns. I'll just share my screen now with you. Okay, is my screen visible?
Yeah, all clear.
Yeah.
All right, perfect. Okay, so today the agenda of this session is to firstly understand what threads are. So we will be going through some definitions. Most of these definitions are not textbook definitions. They are more like ways in which we can, then have some design patterns and anti-patterns that often come up in the workplace. And then we'll be looking at some design patterns that we can use using threads, and some of the anti-patterns which are unfortunately, they come up in the workplace when it comes to using futures or threads or any kind of asynchronous processing. And then we'll have a short conclusion. So who am I? I'm Gaurav Sen. I am a founder of a company called Interview Ready. This is a company which specializes on software engineering interview preparation. Currently, we have a course on system design. I'm also a content creator on YouTube, and I have worked as a software engineer in Uber, DirectEye, and Morgan Stanley earlier. Okay, so the most basic part of this presentation is the definitions, and that is the first question: what is a thread? Okay, so a thread, you can imagine it to be like the real thread is a path in the program that you can run through. If you actually take a thread, let's say you take a needle of that thread, you put it on line 1, and then you actually go to line 2 and line 3, and this actually creates a path. If you have individual threads, then they are creating individual paths in that program. As you can see here, the same program maybe, or a particular function of that program can be run on multiple threads. So thread 1 has command 1, 2, and 3. Thread 2 has the same commands. Thread 3 has the same commands. Effectively, it's like an instruction pointer. Okay, what is concurrency? So related to threads, why do we even have threads? Well, because we want to run multiple threads together. Why would you want to do that? There might be a particular instruction which is going to take a lot of time. So to ask the thread to run it in parallel is something that you might want to do. You might also want to make it concurrent, as shown here. Like you can see here, command 1 might be something which takes a lot of time. So then you go to the next thread and you run it command 1 also. Yeah, that's basically concurrency. The operating system takes the time that it has, slices it, and then finds out where do I pick up tasks. This happens, of course, in real time. So it's that's concurrency. How is this useful? Like we said, if you need to make a database call, you can run it on one thread. Once the database call is blocked, you can move to the next thread and do some other things. Maybe that will also stop with a network call, and then you open up thread 3. So different lines of execution. Okay, 2 definitions remaining. What is a future? Well, if you have some code which depends on a result, you can effectively wrap this up in a future. So this future is a result which will be run on a thread, and eventually it will respond to you. So if your code is waiting on some database query, then you can store this result in a future, and your code will continue executing, as you can see here, and then periodically checking whether the future is complete or not. That's how we can imagine it. The reason this is good is because you're not blocked again on the database to respond. Maybe the database is in a different continent. It's going to take some time. So you can make an asynchronous call, ask the future to store the result when the result does come in. And meanwhile, you're running other threads. So that is one way in which you can save some, processing power. Or rather, you can respond quickly. So the latency of requests goes down. That's one thing. Okay, so quick run of definitions. I'm sure most of you know about these things. But I have a question to ask, just to probably wake you guys up. When it comes to latency and throughput, is having more threads going to reduce latency, or is it going to reduce throughput? So you can post your answers in the chat. Okay. There's depends on the number of threads, the task and the CPUs. That's actually a really good answer. If you have too many threads, then the context switching will increase to the point that you will almost get nothing done. This is called thrashing, where the CPU is basically running over threads and getting them ready, but before they can execute, you get the next thread in. So if you have a huge number of threads and you have very few CPUs, or if you have very few cores, then your latency is really high and your throughput is really low. But in general, if you want to increase, yeah, exactly. So generally, multi-threading is useful for reducing latency, because what happens is if there is any kind of a blocking task, then you're going to move on to the next thread, and that's going to help reduce the response time of the other request. This is not very good for throughput. So if you don't care about latency, if people are not looking for your response, like a batch process or something in the background, you can focus on throughput, something like garbage collection does often. So you run few threads, you don't overwhelm the operating system with threads, and you're okay with low latency. I mean, with high latency. Okay, so let's move to the next section, which is design pattern number 1. Okay, I'll just start sharing my whiteboard here, because this explains what we are going to do. The first design pattern is causal ordering, and I'll just define that now. Okay. So when we talk about causal ordering, what we mean is that a task. Okay, I have a lot of diagrams here. Okay, so let's say we have 3 tasks, A, B, and C. Let's say B depends on A executing first. So you need to debit $100 from A's account only before you have added $100 to B's account. So A is transferring $100, let's say, to B. That's the idea. But C can occur at any time. Maybe you're debiting $50 from C's account for some penalty. Over here, you can see that A and B are tasks which are causally ordered, which means that B depends on A executing before it, but C can execute at any point in time. So the possible ordering we have is A, B, and then C. We also have C, and then A, and then B, and that's it. Or we can also have A, C, and B. Yeah. So C can occur anywhere. The problem is not this. The problem is when B occurs before A, BAC. That's something we want to avoid. Or this scenario. So how do we avoid this situation? How do we avoid B from occurring before A? If you have a multi-threaded environment, you might be sending these tasks as you get them, A, B, and C, to different threads. So let's say A goes to thread 1, B goes to thread 2, and C goes to thread 1 again. So we have 2 threads now. B may execute before A completes. And that's the problem that we are trying to solve here. The way we can causally order this is by ensuring that the tasks fall in the same thread. Okay, and why is that? Well, because a thread is, like we said, a line of execution of the program. It cannot deviate. It cannot skip some lines and go ahead, or it cannot cut off some lines and go back. It has to go linearly. So when you're putting it on the same thread, effectively what you're saying is that A has to execute here. After that, sequentially, once you're done with this, put in B, execute this sequentially. So I'm assuming that, of course, there's no asynchronous tasks happening inside them. If that happens, then you have to ensure that these things also complete before this. So you can also take these asynchronous tasks and put them in the same thread out here, in which case this will become like A, and internally those tasks will become subtasks like A0, A1, and A2, and they'll be running sequentially then. That's the general idea. Why is this useful? Well, because if you need any kind of causal ordering, you don't want total ordering. You don't want all of these 3 threads to fall in the same thread. All of these 3 tasks rather to fall in the same thread. If that happens, then, well, like we said, our throughput is going to probably increase, but our latency is going to be very high. Maybe B has a lot of database queries, which C is not related to. So we could have run C, but we are just running B sequentially. So we are introducing ordering only where needed, and we are introducing concurrency wherever we can use it. That's a good principle to keep when you're running a production system, with multiple threads and multiple tasks dependent on each other. Okay, can anyone tell me in code how are you going to do this? How are you going to assign a particular task to a particular thread? Like, what would be a design pattern for this? This is the idea. This is the general idea. How do you actually do this in code? Okay. One of the suggestions on the chat is an alternative seems to use join rather than putting in a thread. This is also fine, but the join actually it waits for a thread to complete execution. So yes, you can ask this thread to wait. In my opinion, there's an easier way to do this bit. Okay, extend thread. You could extend thread, but there's a particular data structure in Java which does this for you. So it doesn't extend threads, but it handles the thread execution. If you have a look over here, we don't really want to change the behavior of a thread, in which case we would like to extend the thread object. We would actually like to just use this thread and have some sort of a manager which manages which task is falling on which thread. Yeah. Executor service is the answer. We have a special kind of executor service. The basic executor service, which is provided in the Java libraries, doesn't do this. What we want to do is we want to keep some sort of a hash map effectively. If A or B comes, then you want to put them in the same thread. So this is some sort of a key. They should be able to hash to the same key. If you hash A or B, it gives you the same key. And if you hash C, then it gives you a different key. So that's key 2. That's it. This is key 1. With that idea, what's going to happen is these tasks, which you want causally ordered, will fall on the same thread. So that'll be A and B here. And when C comes in, well, it can go on a different thread. And what we are doing effectively is, if you have different threads here, you care about causal ordering of the people who are falling on the same thread. How is the executor service helping over here? One of the things that you can do is you can assign this task to, instead of a thread, an executor service. This is helpful because the executor service might have a thread pool in itself, and you can keep it a single thread pool if you want perfect ordering. You can use a single thread per executor service for perfect ordering. Or if you are okay with some sort of concurrency where A and B don't need total ordering, maybe their database queries can go in different times, but they have to be accepted one after another. That might be some sort of like very specific ordering that you have. I've never seen this in the production system, but yeah. So, but if you do have that, you can put them in the same executor service. And if C and D have total ordering, you just put them in a single threaded executor service. Now, when C and D run, they'll be running in total order, but they're not related to A and B. Okay. So I have actually created a data structure around this. I have seen this happening often enough in companies, and I'm sure somebody must have an open source library for this. But the one I've created is called keyed executor. It's a very basic thing. It just has a hash map to executor service mapping, and you can causally order your tasks based on the hash that they give. Okay, that's one design pattern. Anyone having any questions on this design pattern? How is it useful? Well, it helps you order tasks according to their relation. But anyone seeing any issues with this keyed executor design pattern? I don't think I have documentation on it. I could check it on GitHub. It's available on GitHub, and let me quickly go over that. If anyone else has any question, you can put that forward. Yeah, I don't think I have any documentation on it. It's more like I've done this as a side project. I should probably put in a little more documentation around that. But I can share my screen to show you the code. In fact, that might help. Yeah. I think this is visible now. Yes. So we have a very basic executor pool, which is a simple array of executors. What happens here is that I'm taking a single thread executor service. And then I'm just, if I get some sort of a task for this key, then I just say run asynchronously this task in this thread pool. And the rest of them are, of course, just sugar-coated functions. The most important one is get thread for with a runnable task. You can push in a supplier, you can push in a completion stage. All of this is asynchronous. All of them are falling on the same key. It's just that the method signatures are different. And it's extremely simple. It just initializes in like 3 lines, 4 lines. Yeah, I shouldn't count lines when initializing, but yeah. Okay, so let's head to the next design pattern. The first is causal ordering. Threads actually help us make sure that related tasks fall in the same bucket so that they are executed one after another, while making sure that we are also keeping our system as concurrent as possible so that things which are not causally ordered are run on different threads. Maximum concurrency, low latency. That's the idea. The second idea is request collapsing. This is pretty important if you are thinking about rate limiting, if you're thinking about saving resources, reducing network IO calls. And let's see what this means firstly, request collapsing. Okay, here's the diagram. Yeah, I think this is visible now. Okay. So as you can see, there's multiple services that we have. One is the profile service. We have SMS service. There's basically multiple services, and they want to get, let's say, profile information for a particular user. So they're firing, let's say, select queries. Okay, but they don't want to directly hit the database, so they have a global cache which stores profile information for users. So if I give the key, the profile ID, then I'll get the value, which is the profile object. That's stored in this cache. This might be a Redis cache. This might be a cache that you have made yourself in memory. But here's the idea. If the profile service asks for profile 123 and the cache doesn't find it inside it, it's actually going to make a DB call. So that's one DB call. If the SMS service simultaneously asks for a profile, the same profile 123, this might be a popular user, this might be a celebrity. Everyone is asking for the same profile information, and you're fetching it from the database not once, but 3 times. Because the cache checks in itself, every time this message comes here, the cache actually checks inside itself, sees that, no, I don't have this profile information. Let me ask the database for that. And it doesn't take into consideration that it's already asked it once earlier. So the DB queue gets filled up. and then it starts pinging the database, multiple times, possibly, maybe a single time. But there's wasteful IO over here firstly. And the second thing is when you get the result, this cache fills in this key, but the other two requests still wait for it, for their own futures to complete. Okay, so this is not great. This is not a good idea. What can we do to improve it? The idea is request collapsing. When you get a request for a particular profile, what you do is you don't just return, you don't hold on to this request. Asynchronously, you fire a request in the backend and you store a future here. So instead of a profile, you store a future of profile for this ID. Now, if the SMS service says, hey, give me a profile with the ID 123, I'm going to check in my cache and I'm going to see actually a future for this already exists. So here, keep the future. A future is a container which stores results. Which will have its results populated in the future. That's the general idea, right? The problem is the client is not happy with the future. Like a future is effectively useless. Without a value, it doesn't mean anything. So the client holds on to that. It holds on to the future. This client is also holding on to the future. And this client, when it makes a query for 1, 2, 3, gets the same future object. But all three of them are still waiting on you. What's the good thing? Well, as we said, this future object is actually behind the scenes. There's a thread which is executing this DB query. It's going to get the data from the database. So this is a single query, which is going to be executed once. It's going to give a single result, which then is going to release all three futures at the same time. So you have done some IO saving over here. You have probably done some processor saving also. You have released all three futures the moment you got a result for the first future, which is faster than, the calling service sending it maybe 3 seconds later and getting the future a little later. And so overall, there have been savings. Why is this useful? Well, not just for savings. Very often when there is any kind of thundering herd, when there is any kind of a viral event, let's say Black Friday, or let's say a particular thing has gone viral, a meme has gone viral. Everyone is asking for the same meme. You don't need to give the meme back. In your cache, you just store the future object, and then you return the future object when it's finished. So this is a second design pattern, which is request collapsing. If you want to see how it looks like in code, I have a snapshot over here, again from the same repo. I'll be sharing the link for the repo as soon as we are done here. But I think this is visible, yeah. So the important line here is, if the cache does not contain the key, that's not the moment we are looking for. We are actually looking for the cache already contains the future. So it's in this else statement. You can see here that the result is cache.getKey. And the important thing is you just return this. Okay. So if the cache contains a future object, completion stage is a type of future. You can assume it to be that because I'm using a completable future in this code, and completion stage implements that. But if it contains the key, then just get it. If it doesn't contain the key, well, then you need to do this bit, load from DB, which is going to take some time. So this is a new future object that is being created here. Okay. And the other thing is, this cache also has a keyed executor. So if you're doing any kind of update, or if you're doing any kind of query, then you need to run it on the same thread. So that's also happening, like this stuff is happening on the same thread. If there is A and then B and then C, which depend on each other, then this method will be called in that way. Internally, we are returning the same future object for the same query. Is this making sense? The basic idea is actually really simple. We don't want to repeat work. That's the basic idea. Add to cache, well, does it need to be synchronized? No. The idea here is that if I look at add to cache, if I zoom in on it a little bit, it actually has a key. So it's not the best API in the world, for add to cache, because adding to cache should be just a value, shouldn't be dependent on a key. But what I have done here is that just to highlight on how this keyed executor concept works, you can actually say add to cache. Well, if you're for this key, then run it on this thread. So load from database is the thing which is doing the actual work. The key over here, this key, is the one which assigns a particular thread for this work to be done. Ideally, like I said, you don't want such a low-level API to make sure that it runs it on the thread that you're asking for. Maybe synchronizing it is a good idea. You can try some other threads like locks is also a good idea. But yeah, this is also another way that you can make sure that they're ordered. Okay. I'll just wait for 1 minute in case you guys have any doubts on this. All right, let me share the presentation again, because we are heading to anti-patterns. Okay. Anti-pattern number 1. So till now we have seen the good things about threads. Okay, there's a question. So what is what is the benefit of using this keyed executor versus only executor service? We are building on top of it. Yes. The reason we are using a keyed executor in this particular case is because, yes, the general idea is that we want the add to cache command to go in the same thread, right? Okay, anti-pattern number 1. This is an interesting anti-pattern. Both anti-patterns that I'm going to talk about, like most anti-patterns, are not such a big waste of resources or are not very harmful for the computer as much as it is for the developers who are going to be reading that code. So the first one is the execution rabbit hole. And I'll just I'll just draw this out. Okay, so here's the general idea. If you have used listenable features from Guava, or if you have used the basic feature objects, like there were callables also, which used to be used. This is like 5 years ago, approximately. There used to be objects called futures, and they still are. I mean, they've just been extended and improved on. But the future object, just a second, guys. Yeah, the future object can either succeed, in which case it completes, or it can fail for various reasons. There might be a timeout, there might be an error while running the task. You might get an exception from the database. The object can fail, in which case there are 2 possible paths of execution. If there is a completion, successful completion, then run this code. So if you get the profile, then ask for a session. Now this is also future, right? Because you're going to be asking the session service for some information. So this is being backed by a future which says complete, or you might actually end up failing. If there's a failure here, let's say we just notify. And we do the same thing here. Similarly, if there is a completion, then go to the payment service and make the payment, which again is a network call. So that will be wrapped in a future, so that the network call doesn't block the rest of the resources, the rest of the threads which are coming in. But you're seeing the problem happening in the diagram. The problem is that this is a pretty complex tree that is being built. And in code, what ends up happening is that you actually call this future, which is call profile service. Internally, the profile service, if it completes, right? If it completes, then it goes to the session service. So what ends up happening is call profile service contains the code for completing this session service. Call session service will internally keep the code if it completes of calling the payment service and so on. So if you have multiple services that you're calling, the code is going to be having the if else condition of passing or failing. And unfortunately, because you have that inside this code block, when you call that function, it itself will have a code block of if and else. If is the good scenario, else is the bad scenario. And again, there's going to be another code block. So this is a rabbit hole of futures. It's happening not because you have very poor programmers, or if you have people who are not calling the method in the right place. It's happening because there are two possible scenarios which we have to deal with in any future. Okay, and if you try to flatten this, if you try to make it in one line in the same place, then the method becomes extremely large, and you want to avoid that. So is this problem clear? And does anyone have a solution for this kind of a problem? The problem is occurring because usually when you run a command, it's expected to pass. And if it doesn't pass, it just throws an exception. While a future, unfortunately, has two possible scenarios. It can give you two results, either a pass or a fail. And yeah, okay, so there's one suggestion. Why not factor each step into a function and make it throw an error if failed? Then call all of them in succession in one try catch. Okay. Why not factor each step into a function and make it throw an error if failed? All right. But how are you going to, the problem is how are you going to chain them? That's another problem with the future object. When you say that, let's execute task A, okay, call from the profile service, then execute task B. This is a problem. It depends on task A to finish. So this result has to be actually picked up from this, this task, put into a future, let's say profile, and then B has to actually take this profile. Okay. One idea would be to actually, okay, there's a few suggestions. I'll just go ahead with this for a little while. One idea would be to actually pass in a future of profile to this method, and then you can take a future of sessions here, right? When B completes, only after this future of profile is finished. And then, but even there, we are going to have a if-else condition. If the future fails, then do this. If the future passes, then do this. Okay, you can call is done before asking for the next one. Okay. Is done on this profile object is an idea. What we want to do is we want to sort of chain them together. We don't want to check for the future ourselves. We don't want to make sure that is it done or not. So a future object ideally should store the result and should continue executing. Like it should execute asynchronously without us knowing about it. If there is something that we want to do after the completion, then we should probably add some sort of a listener, or we can chain futures together that this future runs after that one. Okay, there's another suggestion. You can store them like an event. So once this is done, so let's say we have a publisher subscriber kind of a model, or just sort of a message queue will also do, where we take this profile result and we put it in this queue. And whenever a profile comes in, we actually send it to a session call. So this line of code is going to execute. This line of code is basically something like a subscriber to this event. That is also an idea. Yes, we can do that. The problem can be avoided to some extent. Callbacks is another thing. Callbacks actually, in my opinion, it leads to this problem. When you do a callback, you say that when this happens, please let me know. So on success, on failure, the problem is on failure is a piece of code where we have to write exception handling, and on success, we call the next task. So profile, on success, session, and then we go in the method of session, and then it has its own on success, on failure. So on success of session, okay, payments. So it like really nests itself up. It becomes a proper rabbit hole. Futures, callables are, in my opinion, the biggest culprits for this thing. There is one object which you can use, which is not very recent, but solves this problem in a really interesting way, which is completable future. What this does is it actually allows you to chain futures in a nice way. So for example, if you have get profile, and I say 1, 2, 3 here, I can actually say after this is complete, when this completes successfully, then apply 1, 2, 3. So you just get the result here. Then you apply the result to the next part of your code execution. So that might be get session with this result. Okay, the result, of course, is profile. And then you can chain another future which says then apply. This is going to be a session that you get as a result of this future. So then apply session get payment, where you pass in this session object. Okay. Technically, this is going to be then composed, and this is also going to be then composed, but we can ignore that. It's basically a then method. If this, then do this. What about exceptions? Like, these are all the happy parts. They are being taken care of. If you have an exception, then you get the exception right here. Okay, what technically happens here is that when you do a get profile, if it passes, this runs. They put it in a stack. There's a stack where we are putting in different things to do. Then you say, if that happens again, then apply this part. So in this stack, firstly, get the profile. Okay, then, so I've drawn the stack inverted actually. Firstly, get the profile. Then you get the session. Then you get the payment. That's the idea. So you're kept futures dependent on each other. The other thing is, if there is an exception on any one of these things, any one of these points, let's say the payment didn't go through correctly, you get that exception in the exception part. Okay. If there is an exception, this does not run. This does not run. In profile, if you get an exception, these two methods will not run. If you get an exception in the sessions method, this method will not run. You'll just head directly to exception. Yes, absolutely. This is a pattern similar to promises in JavaScript. Most languages where where you can chain futures, the problem of the rabbit hole goes away. Java recently did this. However, there is a lot of production code even today where we end up using futures in on success, on failure kind of patterns. So to increase code readability and also to clearly see like the graph of futures that you have, there's a code execution graph that you can make. Once A happens, then B should happen, and so on. That is much more clear if you actually chain futures, right? If there is an exception, then handle it. The only problem here is that the exception handling can get complex, because instead of having one type of exception, which is in get profile, you might have 10 types of exceptions here. If you have 10 futures, the exception might have any of the 10 exceptions. So it kind of depends on what you want to do. But usually the exception is handled in the same way. This entire operation, if it's just a single operation conceptually, then you can deal with it with just one response. We are sorry to the user. You can send a apology email. You can retry the same thing again. You start from get profile. Maybe the session service didn't work out, so you can just retry the request. That's one thing that you can do in the exception thing. Or you can put it in the dead letter queue. Whatever be the solution for this. If these are basically chained operations, you can chain them by taking advantage of the language itself. Then compose, then apply. some of the good things about this is you can actually run it on different threads also. So then apply async is one way you can do that. You can run it on a different executor service. So yeah, on the chat also, you could have one thread just handling exceptions. That is true, but I wouldn't suggest that. What happens normally when you say then apply is that it runs on the same thread. And usually I like that unless you have a specific reason to run it on a different thread. Let's say you want to make a database call, you have a thread pool of database. I mean, you have a database which has its own, you have a thread pool which makes queries to the database. Okay, that's one thing. You might have a thread pool which is making queries to a particular service. So in that case, yeah, you can use a different thread. But if you're going to handle exceptions, you can handle it on the same thread. Because anyway, the caller of this is going to be waiting on that future. So if you handle it on a different thread, the exception will be missed, possibly. In this callback, in this future, right? Can we parallelize the treatment inside the block? Yes, you can. One of the methods that you can use is completable future, provides you a lot of chaining around asynchronous listeners. So then apply async. Please do this task, which is call session service, but don't call it on any thread that you want. Use this executor service to actually run that. So future dot then apply async will do that. You also have async for then compose quite a few things. You can also have a listener called when complete. So you don't really want to do anything, but you want to run the when complete of result/exception, and you want to deal with it right here. If you want to get rid of the exception, then you can also use instead of when complete, you can use handle. Right over here, what happens is whether it's success or failure, you have to return a result. So you want to deal with it. Okay, you can have a look at the Java doc for completable future. It's a very useful class, and it's definitely something we should move on to. It does take care of an entire anti-pattern by itself. Okay, the final anti-pattern, which I don't think I'll have the time to get into in detail, but the general idea is don't use futures everywhere. This might sound like, what is this kind of anti-pattern? It's not real, but actually it is. If you're going to use a cache, let's say an in-memory cache, and the idea is that, well, I'll actually just share my code over here. This is something that I have seen happening on production, so it's something quite interesting. Yeah, this code, for example, it is returning a future whenever you are saying a get or a set. This is not always necessary, right? If you do a get method and you don't get it, if you don't get this particular value in the cache, you don't need to return a future. Always, you can decide not to do request collapsing. That is one way you can do it. Sometimes you just want to check in memory. If it is not in memory, then you fire a DB query for which you take a future and you return it to the client, right? The problem of using future everywhere is that firstly, the wrapping and unwrapping of future objects is pretty painful. That kind of extensibility is not needed. If the idea of the cache is to be in memory, instead of having some database backing it up and keeping it consistent, you don't need future objects. You don't need asynchronous calls. In production projects, I have seen this happen because people want to make it extendable, because people say that, hey, what if tomorrow it is backed by a database or backed by a service externally? Well, if that happens, then we're going to use it. If you use it beforehand, if you start using futures before you need to make asynchronous calls, the developer has to take a lot more things into consideration, has to actually consider what if this feature fails or passes, when does this feature complete, what if this runs, I mean, asynchronously, it can complete at in any thread or in any point in time. So there's a lot of cognitive overload the cognitive load that a developer has to take every time you write a feature. So only if necessary should we go ahead with it. Okay, I'll just share this. I won't call it open source. I'll say publicly available repo. This is the example that I'm just showing right now, the cache. I'll share it to everyone in the meeting. Okay. These are the main design patterns, like 2 design patterns and 2 anti-patterns that we have talked about today, are the ones that I'm most commonly seen happening. Whenever you need to make an API, if you use a complete feature, that's not a great idea. An execution rabbit hole is a place where you have 2 parts of execution, and you end up going really nested and really deep in one particular path of execution. So for the developer who's just joining your team, they have to actually click and go inside a method and then click and go inside the next method, and it takes a long time for them to actually go down this stack of execution. Not a great idea. We talked about design patterns. One is request collapsing, where we ask for the same request or the same object just once to the database, but in front we keep a future object to keep everyone else waiting. And causal ordering. This is probably the most common and the most important point of threads. Okay. So if you're looking for more content around concurrency and around system design, I have a YouTube channel. It's all the videos there are of course free, and you can have a look at that. There's some tips that I've written down. So around immutable objects also, they're not silver bullets, but yeah. It's ended quicker than I thought, but we have 3 minutes, guys. If you have any questions, do let me know. We can try to sort them out. Christian is asking, can we go reactive to sort out all these threading issues? Well, whenever you have some sort of a subscriber model, or whenever you react to events, there has to be the infrastructure around to deal with it that way. I mean, it's not a bad idea. It's actually something which occurs often enough to make us think whether we, I mean, if Java should look into this, should look into reactive coding or programming to help people deal with future objects in a better way. I think they have completable future now, which is pretty useful. If you want to have some sort of a notifier or a listener for every time a result comes in, you have objects for that. You can have a notifier object. Complete future actually is technically doing that under the hood. So it does notify you whenever there's a then apply. The thread actually picks that up. So yeah, well, one question is, can you briefly describe the relationship between throughput and latency? Okay, maybe I misspoke there, but I'll clarify again. If you have a lot of threads running, what's going to happen is every time the operating system chooses another thread of execution to run, there's going to be a context switch. There's going to be, okay, I was on instruction number 10, now let's go back to instruction number 5. So that takes some time. And it's not just a simple instruction move, it's also some data structures have to be updated. So the more number of threads you have, the more the operating system has to juggle around, and juggling or multi-threading or context switching has an overhead. So the throughput, which means the amount of processing, the amount of work you're doing per time slot reduces. But the latency can go up, because if you need to get a database request, right, you need to get an answer from a database. So you ask a thread to do that, and then you stop the execution and start the next thread's execution. Maybe you can finish thread 2's execution, give lower latency, after which you can go back to thread 1. So I don't know, I can take such a simple example. Count up to the first 10,000 numbers, wait for user input. If you run wait for user input, it might take forever. But counting for the first 1,000 numbers, you can do that sequentially. So if you run thread 2 first, and in between keep checking for the user's input, then both programs will be happy. It's a fair share of the time instead of just waiting on one person. All right, final question regarding the point with immutable objects. Are there notable anti-patterns with them? Well, yes. One of the anti-patterns is that if you have an immutable object which is being mutated a lot of times, then you have to recreate that object. There's no way to actually mutate a immutable object without doing a create operation with the mutation in the constructor itself. So if you have an integer object, let's say an integer wrapper, 10 plus 3, well, you can't have 13 in the object. You have to actually create a new object with value 13. So if you take a big graph where you want to, you have multiple threads which are updating that graph or that tree, you might have this often in analytics, then keeping immutable objects is not a very good idea, because multiple people are going to be updating that anyway. And if they're going to create, let's say, hundreds of objects or thousands of objects, and you're doing this very often, this is going to take time. So have it mutable, but try to constrain the paths of execution or the ways in which different threads can be accessed. In this case, it's more engineering intensive, but it's worth the cost, engineering cost. Okay, this is great. All right, everyone, thank you so much for coming. It's been awesome talking about threads. It's something that I think a lot of us use in our day-to-day lives, and some of these anti-patterns are rather obvious, and some of the design patterns, though, are very useful when we are thinking of actually solving, commonly occurring problems. Thank you, and I'll see you next time.